Okay, let's get started. Hello, everyone. You're not going to hear the speakers. This is just for recording, so don't be surprised you can't hear them through the speakers. My name is Ramin. I run Cambridge Game Creators Network. You've probably heard of it already since you're here. I run this network with 7 other friends of mine. We started this initially to focus on games, hence the name, but we had a different vision from the beginning, and the vision was we wanted to make this more about computer graphics and visualization, which is not just games. Of course, there are other industries, for example, simulation, scientific computing, computer-aided design, and a lot of other subjects that are not games, but in an interesting way, they actually all share the same type of technologies behind the scenes. So with today's event, actually, this talk that we have, thanks to Mark here from Cavendish and Professor Mike Payne, who can't be with us today, unfortunately, we have kind of made that vision come to reality. So a big thanks to you. I wanted to actually make an announcement today, since most of you guys, I'm seeing most of you guys for the first time. You're not a member of CGC. For that purpose, I think this announcement is being done at the right time. But before I do that, I actually want to ask Mark to do a short introduction of what Cavendish is all about. Some of you are students, I know, but some others are coming from various different companies and universities, so I think it's best for myself and everybody here to hear first Mark to introduce Cavendish and what they do here exactly and why we decided to basically host this event at Cavendish. And then after that, I'll continue to the announcement and we move on to the main talk today.
Okay, thanks, Ramin. So I'm Mark Hayes. I'm the director of the eScience Centre. We're based here in the Cavendish. And the Cavendish itself probably needs no introduction. It's one of the largest physics departments in the country and one of the most well-known, both historically and for its current research. One of the sort of newer groups we have here is the Centre for Scientific Computing, of which I'm part. And that has a role to sort of support scientific computing in general across the university. And just briefly, this is hopefully the first in a series of events between local academics and local industry centered around GPUs and scientific computing for them. I should say also, or we're asked to say, that if a fire alarm goes off, we're not expecting one to, then the fire exits the 2 doors here at the front, and there's one at the top left of the room as well. So I have nothing further to add. So, Andy? Yes, or you can introduce Andy first. More, yes. There you go.
Right, so Cambridge Game Creators, or CGC, we, together with a media or news company in Cambridge called Kaboom, you might have heard of them, we together started planning a bigger event towards the end of this year. This event is what I wanted to announce. It is called Mosaic 3DX. It's going to be a trade show / conference where companies from across the UK, and hopefully we are trying, and we have been successful so far, to bring in companies from other parts of Europe and the world to take part in this event. What this event is going to focus on is actually different applications of computer graphics and visualization. So you guys are here probably because you either work on the technology, on the graphics technology, or you have an interest in kind of scientific or medical or kind of technological engineering applications of graphics. But there are other groups, other industries, for example, gaming, visual effects, artists, arts and design, a lot of different industries that have an interest in the same kind of subjects. So this event is actually trying to bring together all these companies, and hopefully this will be kind of a very kind of exciting event for anyone who will take part. I mean, actually, today's event shows that we can apply these technologies to a lot of different applications. Our previous events have all been focused on games, but today we have less game developers here. We have more of those who have different types of interests. So if you are interested in this, please go to, this is actually, I wanted to mention, in collaboration with Microsoft Research in Cambridge. So this will be held at Microsoft's new building on a station road. So if you are here still in October, it would just be a 5 minutes on a taxi or 10 minutes, 15 minutes on a bike. We are designing it for everybody, so it won't need, you know, big cash to just register. So this is kind of being designed for everyone, students, hobbyists, as well as professionals who are supported through their companies. If you're interested, please go to mosaic3dx.com. The main site is still not up. We haven't published it yet. You can register your name and email. As soon as the site is up and the registration opens, you will get a notification. So that was my announcement. Now back to today's event, today's talk with Andrew. I don't want to get into too much details of, you know, how GPUs have affected everybody's lives. I mean, every single phone, tablet, mobile device, portable device, or laptop today has a GPU in it. A lot of you have already heard about what a GPU does, what it is all about, and if you haven't, today you're going to learn a lot more. But I'm honored that we have Andrew Rickards today, who spent a lifetime actually making this technology available to everyone. I think his area of focus, OpenCL, is something that is trying to do that, trying to bring this technology and make it available to everybody, not just those who understand hardware really well, but also those who just want to use the technology for their advantage, be it scientific research or gaming or arts. So I'm honored to have Andrew here, and please welcome Andrew.
Thank you, Raman. Can everyone hear me? Can you hear me at the back? Good, right, okay. I'm not very good at speaking loudly. This is just a recording, isn't it? There's no speakers, right, okay. So I'm Andrew, and I run a company called Codeplay, which is based in Edinburgh, in Scotland, and we build compilers for GPUs. So it's quite a specialist company that I run. We're about 26, I think. We're growing quite fast, 26 very geeky, techie people in an office in Edinburgh. So what we do is quite unusual, and so it's difficult for me to work out exactly how to pitch this talk. So what I'm going to do, I want to ask people what kind of background and what they were hoping I would talk about today. And I'll see if I can hastily edit the slides to make it more about. So the first is, how many people here are students? Okay, quite a few students. How many, just check it, how many people are studying computers rather than, okay, none of you are studying computers. Okay, this could be bad. Right, but science, how many people, right, okay. How many people are game developers or, you know, hobbyist, it's all hobbyist game developers nowadays. There's not many professional game developers left. Oh, right, okay, one, okay. People design GPUs. See, there are a few, right, okay, that's good. How many people don't know much about computers but like playing on PlayStations? Good, good. That was that was my big fear. Okay, okay, good. Sigh of relief. Right, okay, so. Ooh. This is always the embarrassing bit where, you know, you have techies giving talks and they don't actually know how to set up the screen. So hopefully this is going to work. Is this going to work? Oh, wow. That's good. Okay, so what I'm going to talk about is give you a flavor of all of the crazy things that are happening in GPU computing at the moment. And I'm going to cover a lot of stuff because there is a lot going on, and I'll try and drill in on some things and explain things. And how long have we got? We've got about an hour, and then questions or something. So I'm expecting a few questions, maybe. So I'm actually going to start. We run a geeky company, but actually I have to do the sales as well. So I'm going to start with a bit of a sales pitch. So the first thing that Mark said is NVIDIA turns up and they show us these marketing slides. Well, I'm actually going to show you NVIDIA's marketing slides at the beginning of my presentation. But then I've promised to get into what it actually means. So one of the things that is happening at the moment is the GPU is taking over from the CPU. I mean, it's taking over in the sense, I should be careful, there's people from ARM here, isn't there? Well, you do both, so it's okay. There's no one from Intel here, is there? Good. In terms of importance, I'm going to, in terms of innovation and a whole load of reasons, so I'm just going to give you a sense of this. So this is quite an old marketing slide from NVIDIA showing you the importance of GPUs. And what it's showing, this up here is, I can't even read it anymore. 2007, the supercomputing, which is this high-performance computing show floor, and the number of companies talking about GPUs, which is 1. And then 2011, the supercomputing exhibit floor, the number of companies talking about GPUs. And what you'll see is, in terms of mind share, in terms of what people are talking about, in high-performance computing, it's all about the GPU, and it's happened incredibly quickly. Oh, yeah, go.
I don't know how good or bad it is. Is this better? Or?
Is that better? Right, okay, good. I can't see you pulling faces at me now. And this is going up in supercomputers. Now, I'm not entirely convinced that this is actually a good business model, because a lot of companies have got the latest, best thing in high-performance computing and then gotten bankrupt very quickly. But anyway, it's definitely, in terms of what people are thinking about, in terms of researchers, in terms of what people are talking about, GPUs are very important. This is the slide that matters most to me, because actually what Codeplay does, I used to be a game developer, and I quite like to still be a game developer, but we do this weird stuff now. And so mobile is actually most of what we do. And so this is the Apple chip, right? This is what they stick in their iPhone and their iPads. So this is one of the most manufactured chips in the world. I mean, they sell huge quantities of this. And the A4 is, how many years ago? 3 or 4 years ago now. And what you'll see is it was the first chip that they totally designed themselves, pretty much. They bought some bits in, but the CPU and the GPU are roughly the same size. A year later, the GPU is a little bit bigger than the CPU. I'm trying to remember, that might actually be 2 CPU cores, which gives you a sense of just how much bigger it is. A year later, actually it's only a few months later, right? They have a massive GPU, and this is in their iPad with the Retina display, the crazy resolution display. Absolutely massive. It's dwarfing the CPU. Now, my argument would be that, there's a lot of copy and pasting going on in building these GPUs, so maybe it's not so complicated, but it's quite complicated, but it's massive. The computational power in it is massive. You go to a year later, and it doesn't look like there's much difference, but the difference is they've got an absolutely massive CPU core in there. These GPUs are huge in any normal sense, and they're just in these tiny smartphones. I'm going to talk about why. So the first thing, this is horribly old-fashioned, actually. I'm sorry, I've copied this slide in from somewhere else, because it's just, this is a few years old. This is in no way relevant to what's going on at the moment. This is just a presentation that I stole from GDC. And I don't know if you'll notice, but there's a little bit of an effect. The light kind of blurs around the edge of the helmet, kind of gives it a glow. And there's a little bit of blur in the distance and a bit more focus close up to try and highlight. It focuses the eye, in a sense, on part of it. It's just a tiny little subtle effect, but it makes the whole thing look much less like computer graphics and just a bit more real. At 1080p at 60 frames per second, that's 23 gigaflops of computing power. Now, that's not very long ago, that was kind of high-performance computing territory. And yet, all it's doing It's just a little bit there, a little bit there. This resolution is no longer relevant because an iPad is what, 2000 by 3000 or whatever it is. This is even a low resolution by today. So just the user interface, doing these kind of things on the user interface, is using this kind of floating point performance for just a little bit of it. It's just phenomenal the amount of processing that can be used up by very, very simple graphics. So, why are GPUs taking over, right? And one of the reasons is, what we find is, once software is parallel, you might as well make it very parallel. You know, if you can parallelize it, you might as well parallelize it a lot, okay? And that's the reason in terms of it's easier to do this kind of programming. I'm going to come back to that. But the other reason is the business reason, right? Which is that if you make a massive GPU, it runs last year's graphics software twice or 3 times faster, right? You can market that. Whereas if you put twice as many processor cores in on a consumer device, it has no impact whatsoever. In fact, it probably just runs the battery out faster. Unless people have written special parallelized multi-core software for the CPU, there's no real benefit. And so from a marketing point of view, it's much easier to sell chips that have massive GPUs than it is to sell massively multi-core CPUs. Now that's probably different in the server, where they've already parallelized it, right? Because server software, web servers and stuff are already parallelized. But in consumer electronics, it's very hard to sell more processor cores other than saying there's more processor cores. It's very hard for anyone to see a benefit. Whereas for GPUs, there's a clear benefit. What I was going to say about this top thing about once software is parallel, it might as well. When we started talking about parallelization, I used to talk a lot about Amdahl's law. Those are your students. Will you be studying Amdahl's law? You must be studying Amdahl's law. So Amdahl's law is that if you only parallelize 50% of the running time of your application, the maximum performance improvement you can get is you can double it. It's very much the glass half full in that there's not much you can do really. If you have to parallelize a huge amount of your application to be able to have any impact. And so you've got to look at your applications and go, can I parallelize almost the whole thing? Otherwise, it's not worth the effort. The pessimist's way of looking at it. And then there's another law called Gustafson's law, which is the optimist's law, which is if you can parallelize part of your application, what you should do is do that bit. It's good marketing sense as well, actually. It's good business sense to go, all right, okay, what we'll do is we'll just parallelize this. We'll just give up on the other stuff. We won't bother. And that's kind of what's happening. We're following Gustafson's law rather than Amdahl's law, which is, I don't think Gustafson's law is actually taught in universities, but commercially it's the thing that's important. But the other thing that I'm going to come back to is the importance of power consumption. I haven't got smartphones on here because I haven't quite worked it out yet, but I should put smartphones on here. But what I'm going to show is, for most of computing, going all the way back to the point when I started writing games on the ZX Spectrum. I should say, I probably shouldn't say when the lecturer's in here, I did actually study physics here in the Cavendish lab. I actually spent all of my time writing games on the ZX Spectrum, so I don't actually remember very much of this lecture theatre. But anyway, right, we'll just pretend that never happened. Don't do what I did. So what happened in those days is that on the ZX Spectrum and ZX81, the power consumption was very low and the clock rate was very low. It was between about 1 and 4 megahertz. Seemed like a lot at the time. And the chips didn't have heat sinks. They didn't have fans, they didn't have heat sinks. You just had chips soldered on a board. Right? That's all it was. There wasn't any power to dissipate. And then what happened over time is just the clock rates just went up and up and up and up. And if you were a sensible company like Intel, you predicted that. That's where Moore's law came from. It's just going to go up and up and up. And you got on this conveyor belt of just, right, we're going to have a pipeline of chips. Every chip is going to be faster than the last one. We're going to increase the clock rate from the last one. And what people didn't entirely realize was at the same time the power consumption was going up. And, well, they knew the power consumption was going up. They put bigger heat sinks on it, they put bigger fans on it, and it didn't really matter. And then if you look at the clock rate, it kind of stops about 3 gigahertz. And if you look at the power consumption, it goes up to about 200 watts. And there's a little bit missing from this graph, right? You shouldn't be filming this, but anyway, there's a bit missing from this graph, and actually it goes up there. It never came out publicly. Basically what happened is a lot of people designed processors that just went up here and up here. And people like Intel will sometimes talk about it privately. They'll talk about having a very painful time of designing an 8 gigahertz processor, a massive long pipeline, and taking it to the PC manufacturers and said, look, we've got an 8 gigahertz processor, it's absolutely fantastic. All you need to do is stick a 1 kilowatt power supply in it. And they did actually take it to the manufacturers. And it went down very badly. It went down very badly. And what happened is you hit a limit. And it's the same. It happened all across the industry. There were some other people who also did similar things, you know. A lot of the processors that you see over certainly this period of time, sometimes later, were designed to go above 3 gigahertz. There were certain processors in games consoles, for example, that were designed to go at quite high clock rates. And they got them back from the fab and they stuck them in and discovered they would use 600 watts, 1,000 watts or something. So, everything changed direction. Intel sorted it out very fast. They actually took their laptop processor core, which had been designed out in Israel, and made that the basis of their whole platform. So they totally chucked out their old CPU design, all their old methodology, and just went, right, we're going to take low power designs. And for the low power designs, it means you keep the clock rate low and execute a large number of instructions per clock. So this is it. 3 gigahertz is pretty much the limit. It's unclear that you will ever see in any reasonable application a CPU that goes faster than 3 gigahertz. What I need to add to this graph at some point is I need to put smartphones in, because smartphones actually, they only go to about here, like that, in terms of power consumption. It's not very much. But the clock rate is just going up like that. But we're actually not far off smartphones hitting 3 gigahertz. We're really not that far off. And of course, they're going to have to stop as well. So, the thing about a GPU is a GPU is able to deliver incredible performance per watt. And I'll come back to another NVIDIA marketing slide because it's actually really, really good, this one. It's, you can see the original presentation, right? It doesn't say very much, and this slide doesn't say very much on it, or it doesn't look like it does, but it's actually telling you everything that you need to know about GPU design. This here, this tiny little green thing, is a 64-bit double precision floating point unit. Now, when I started, a 64-bit double precision floating point unit didn't come in one chip. It came in several chips, right? But anyway, now it's just a tiny, tiny little bit on the chip. But what matters is it uses 20 picojoules to do a double precision floating point operation. This here is reading a register, and it uses 26 picojoules. So when you do a single precision, I mean double precision floating point operation, it actually uses more power just to read the input data from the registers, which is the fastest, easiest way to get data into the floating point unit. The actual power consumption of the operation itself is very small. It's only slightly less, but it's less than the lowest cost of getting data in. This here is a small 8K static RAM, right? So it's a small on-chip memory. So it's near the double precision unit. And it uses 50 picojoules, so what's that? 2.5 times as much power to load, not from normal memory, but from a special purpose small memory. What's that, 10.5, 10, 15 times as much? 12 times as much. To read from a slightly larger one. It's a slightly larger memory. Getting the data from the edge of the chip, not off chip, from the edge of the chip is 50 times as much power as doing the operation. Using a really efficient memory access is nearly 1,000 times more power than doing the floating point operation. Now, that is completely, totally, utterly different. That's several orders of magnitude different from when I started writing computer programs on the ZX Spectrum. We're actually using almost exactly the same programming languages as we were using when I started programming on the ZX Spectrum. So our languages have no concept of this. This diagram, which has several orders of magnitude difference, is not in any way represented in our understanding of how to write software. And yet it's absolutely critical to our ability to deliver software on today's and tomorrow's platforms. This is what's impacting everything that we're doing. And we, as an industry, don't entirely know what to do about it. So what we do is you have to control the data movement distances. You have to expose it to some level to the programmer so that it can be controlled and minimized. And so we have to make things a little bit more explicit so that we force data to be nearby. But it's something that's new. It's something that we're still working through. So the summary of what we need to do in the modern world is we need to keep clock rates low and parallelism high, and we need to manage and minimize the movement of data. But the other thing that I talk about a lot is we need to enable innovation, because these are new problems that we haven't worked out solutions for. And so a lot of what I'm involved in at the moment is actually making it easier for people to come up with innovative new solutions in this unexpected area. And what we do is we build software platforms on top of what's called heterogeneous hardware. So heterogeneous hardware is hardware where it's different. You have different compute units. So the simplest will be a CPU and a GPU. The reality in today's platforms is that there's huge numbers of different processor cores on those chips. If we go all the way back, how quickly can I do this? Oh, it's quite fast. Look at all the stuff. I haven't even said what it is. I don't even know what it is. There's a lot of other stuff there that can be programmed. There's a lot of other computational ability that's not very clearly exposed to people. So, that's the reality of today's chips. It's a heterogeneous platform. There's a lot of different processing units on the chip, and the ability to manage data within that environment is very important. But what we also need to do is provide a full range of software development tools. What hardware companies will do, there's one or two in the room actually, what hardware companies will do is they'll provide quite limited programming tools compared with the things that software developers are used to. Software developers actually use a lot of tools normally to build software. Most of the application developers in the world, after all, are web developers or enterprise web developers who are programming on top of Java or C# or stuff. They're programming on very high level compared with, GPU programming. So, how do we actually get software onto these systems on CPUs? And what we do is we layer it. And these layers are very well defined. All of these layers are specified to one level or another. All of these layers, if you're studying computers at university, you will be taught about. You'll be told what these layers look like, what the features should be, and how to implement them. But for GPUs, we haven't really work that out. We are working it out. We're defining it. So how do we apply this kind of layered approach, which allows us to build things of different levels of complexity at different levels, higher levels of abstraction that would go up the system? How do we allow people to build these things on GPUs? And we want to create these standard software platforms, but we also want to enable innovation. We want to enable people to be able to do cool new stuff. And there's actually quite a lot of different systems that we want to be able to program on top of. We don't necessarily know if GPUs are the right way of doing it. They're the biggest thing on the chip at the moment. They're the most powerful thing. They're the easiest thing to sell. But there are other systems that we could use. So, unanswered questions do make an interesting area to be working on. And that's why I enjoy having a company that does this crazy stuff, is that there are a series of unanswered questions. How am I doing for time? I hope I have quite a lot more time because I'm not very far through. 45 minutes up. Oh, we have another 45 minutes. Okay, good. Right, okay, I'm reading the clock wrong. Okay, good, good. So step one, we actually need to build standard GPU layers that we can build things on top of. And that's a lot of my life at the moment has gone from just building random bits of software to going, right, how do we negotiate these standards so that we can build things at different levels? And these are some of the GPU standardization efforts that are going on at the moment. So some of these things are out, like OpenCL you can get, RenderScript, it's quite basic actually. C++ AMP you can get, it's quite basic. Some of this stuff. Some of these other things are on the way. So one of the things that's different about CPUs is that CPUs, we generally work on very standard instruction sets, right? So the two most used instruction sets in the world at the moment are x86 and ARM, both of which existed when I was at university, right? And so for the last, however many years that is, 20-something years, we've had virtually exactly the same instruction set to build on top of. A whole load of stuff's been added, a whole load of stuff's been put on underneath. But mostly, it's not that different. With GPUs, on the other hand, people change GPU instruction sets a lot. And they have good reason to change them a lot, because they keep coming up with new ideas and new capabilities. And so, in GPUs, what we're doing is building a software layer on top. Unfortunately, we're building lots of software layers on top, all of which are incompatible, but hopefully somehow will plug together. But what it means is, with GPUs, you're always programming to a virtual instruction set like you are with Java. So you're always writing to something that's then going to be compiled at runtime down. And there is no way that we could fix that right now. It would be stupid to fix a standard GPU instruction set. But in CPUs, we have this thing called an application binary interface, which is it's a way in which two functions can call each other. It's a way in which the data is laid out in memory, so that if you're programming in C and you define a structure, or if you program in C++ and you define a class, and you define it in two files, as far as the compiler is concerned, there's no connection between those two files. All it does is it sees the same description of what the structure should look like, and so it must match the layout. If it doesn't match the layout, everything breaks in a way that's virtually impossible to debug. And so part of what you do with a CPU is you actually define this. You actually define it differently on different CPUs, unfortunately. It's really annoying. Then you have an operating system on top. We have no idea what an operating system would look like for a GPU, whether an operating system for a GPU makes any sense or anything, or the equivalent of an operating system. So we just add it to a CPU operating system. And then on top of that, we build all the compilers and the debuggers. And they are, the way those are built, they're not really, they're separate components, but they're only able to operate as separate components because everything is defined. All of the interfaces are defined. We haven't worked out how to define those interfaces for GPUs. So one of the problems that we have as a company is that we can never just write a GPU compiler. We have to write everything else at the same time. Everything has to work together. We can't just go, just do that. And that's a lot of what's going on at the moment, is how we negotiate that. But as we go through these standardization efforts, we have an incredible opportunity which we didn't have before. Because we can now build software and tools on top of these standards that we couldn't do. Basically, today, if you wanted to write your own compiler that went on top of a GPU, you'd need to know the GPU, you'd need to choose a particular GPU, you'd need to write it, and by the time you'd written your compiler, which takes some time, I know, I've written a lot of them, the GPU would be obsolete. So that's the great advantage of standards, is that the standard should be around, we hope, by the time you finish your compiler. And so it's becoming much easier for you to actually be able to design languages for GPUs in a way that you just couldn't at the moment unless you also designed your own GPU. But it also enables device manufacturers to design new devices, new kinds of GPU, new kinds of FPGA and all sorts of crazy stuff, and run existing software. We've never really had that opportunity before. If you want to do really complicated parallel hardware, which we've been involved in a lot, and lots of companies have tried, the problem that you have is like before. By the time you've finished porting the software to your hardware, the hardware is obsolete. And that's what's really great that we have the standardization effort, is that you write it on top of a standard. The hardware that you designed it on may be obsolete, but there's a new one, and it should run your software. So all of this stuff is really enabling a level of innovation in these heterogeneous architectures that just wasn't possible before. You wouldn't have been able to do it other than as a theoretical thing in a university. You can actually do it in a more commercial environment. So, what can we build? I'm going to talk about some of the things that we can build, the languages, the tools, and the platforms and the software, and some of the problems. And again, because I build GPU compilers, I'm going to focus a lot more on the compiler side of things and a lot less on some of the other stuff, which may be more interesting to other people. But anyway. So if we bring standard languages to GPUs, so some of the work I'm involved in is making it easier to bring C++ to GPUs. The problem that we have is we have to add in what GPUs do. We have to add in the massive parallelism, and we have to add in data movement. We have to change the language in some way. And that's quite nasty. And there's a lot of discussion about how we do that for different languages. The other thing that's very interesting is most GPUs, most of the time, spend most of the time compiling and running shaders. So when I showed the graphics example before, mostly what they're doing is using a domain-specific language called a shader. And what a shader language looks like, I should have put an example on. What a shader language does is it tells you how to light things. And lighting is incredibly complicated, so you can put a lot of stuff into this. But it's extremely successful because what we have is a language that was designed from the ground up to be run in parallel on a GPU and do just lighting. And so we ended up with a lot of stuff. It's hugely parallel to write in shader languages, and they're actually quite, in some senses, artists doing their own lighting can do bits of work on shader languages. So one of the interesting questions is this parallelism best tackled by creating domain-specific languages for different applications and not by writing standard languages? My company writes standard languages, so I hope it doesn't work out like that. But I suspect that domain-specific languages is a lot of what to do. So could we write a special database domain-specific language that did the right stuff? Could we write a special, what are the other things that we could do? Visualization or visual computing, you know, all of these different things that we could do. Web programming. I suppose web programming has a lot of domain-specific languages. You know, Google have their MapReduce, and there's this Hadoop stuff, and JavaScript can be written, and you know, these things are very successful, and it's starting to become possible to do that on GPUs because of the standardization efforts that are going on. But there's a lot of issues to think about when bringing a language onto a GPU. These are issues. I'm not going to give you any answers to any of these questions. These are the things that you need to think about. You need to be able to call data. Actually, no, I'm just going to. I've got a bit more detail all of them. So one of the things that you need to do is you need to do this strange cross-device function call where the CPU is operating in serial, and then you're running the same task huge numbers of times on a GPU. It's a very strange function call. It's not like a function call that exists in a normal language. And so defining it for a language with semantics in language terms is actually much, much harder than it looks. It looks trivial. It's actually not. The parameter parsing, for example, needs to be very efficient. And defining the way in which you call huge numbers of kernels with the same parameters in a way that works within a high-level language efficiently, where they all receive the data, is actually hard. The other thing that we need to do is we need to be able to glue together two or more compilers. And I'm going to talk a bit more about that. It's another nasty problem. The other thing that we have is that GPUs have a form of parallelism called data parallelism, where you do the same thing huge numbers of times. It's actually very easy. I mean, everyone says parallel programming is hard. And then some people do data parallel programming and go, oh, it's easy. It's easier in the trivial case. Data parallel programming is actually quite easy. Other kinds of parallel programming are very, very hard. And so if you expose an application in terms of data parallelism, you can get massive performance. And so one of the things you have to do is think about, maybe it would be best to expose it as data parallelism, even though it doesn't look like it, and it's quite inefficient. But sometimes you can't do it. This is another thing which we spend a lot of time in terms of defining the semantics of a language. Sometimes the data types need to change between the two devices. So you want a data type, like, you know, say you have a car data type, right? Say I'm a video game developer, right? You've got a car and then you've got 4 wheels and you've got pointed to the 4 wheels, right? So the car's it's got an array of 4 wheels, car. That data type may need to change when it's transferred from the host to the device. Now you still want to be able to operate on the car on the device, but the way in which the wheels are referenced, there's a reference, right? It might be a pointer or it might be something. The way in which that reference happens may be different between the host and the device because the memory model is different. That, at a language level, is a bit of a problem, and we don't have a good way of describing it. And you need to abstract it, but language design becomes interesting. Are any of you here researchers? Yeah, quite a few researchers. See, if you do, these are things that, it's strange, they look simple, and you look at it and go, oh yeah, it's obvious. Well, it's obvious if you're just taking a simple bit of code and translating it yourself for a device. It's not obvious where you go, no, I want to define the semantics of the language so it's the same on every device. So this is the other issue that we have that is a big problem, is you take the same code, but you're compiling it to several different binary formats. And we have a lot of arguments about this, and the two approaches are, one is that you have a single compiler with multiple backends, right? Does that make sense? So the language goes in once, and then it gets converted into an intermediate representation, and the intermediate representation gets taken down to 2 or more binary formats. And the alternative is to have 2 or more compilers that pass over the same source code. And if you're a C programmer, the difference becomes quite noticeable when you do things like hash ifdef. It behaves completely different with these 2 different approaches. And what we found is that C programmers expect the second approach. But the only safe way of doing it and having all the type checking is to do the first way approach. The first approach seems more natural as a compiler writer when implementing the system. But it's actually the second approach is the one that actually seems to work for developers. We have a lot of arguments about it though. Is this working? Okay, this is like an interesting problem for the future. When you look at this problem of how do you have function pointers and virtual functions and you know, the methods that exist in Java and stuff, it looks hard on a GPU. The more you look at it, the harder it gets. It's actually really hard. So if you think about the simple problem, right? A GPU is executing the same instruction lots of times. I'll come back to this. The GPU is executing the same instruction lots of times because that's very efficient. So what happens if you're executing lots of objects in a scene, right? Some of them are cars, some of them are buses, and some of them are lorries, okay? You get to a virtual function, and some of them go, oh, I'm a car, I'm a bus, I'm a lorry. They jump to different places. That doesn't work in the SIMD model of a GPU. Okay, so that's a hardware issue. We can just design the hardware one way or the other, where we can do all sorts of weird stuff, right? But then we get to a problem of, that's if we look at the function pointers. What about virtual functions? I don't know if you know, I should have more diagrams of this to explain how virtual functions work. But what happens is, when you have this thing where you have cars and lorries and buses, and you call a method on them, say drive or whatever, what you have is a type descriptor. So your object, you have all the methods, you know, wheels and stuff like that, number wheels, all that kind of thing. But you have a special hidden thing called a vtable. And it's a pointer inside the object that points to all of the methods. So if you've got a drive method and a steer method and a brake method and a start method and a crash method, right? And you want them all implemented differently, what happens is when you get to a virtual function that looks at the vtable, then it knows, oh, I know the crash method is the third one along, right? So I'll go 3 down, right? Okay, that points to my code. What does it point to? It points to the code on your CPU. It doesn't point to the code on some GPU. Where is it? And so you have a problem of, how do you create a vtable? Now, you might say, oh yeah, well, we're only going to have one device, so we're going to have an NVIDIA GPU, so we're going to say the vtable is changed. So okay, it's going to have the NVIDIA GPU stuff and the CPU. And so you know, third one, we'll look up the NVIDIA vtable. Jump to that one. It doesn't really work, because what happens if you plug a new GPU in there? How does it know which one to look for? Anyway, this is just really nasty. I haven't worked out what the answer is. Garbage collection. This is my interesting one. Here's the bizarre thing, right? So everyone I put this up, right? And everyone goes, well, you're not going to want to do that on a GPU. That would be stupid. Think about it. Which are the applications that you actually want to make go faster? What have we actually done with all of this incredible computation power, right? Because I remember when I had a ZX81, you plugged it in, and instantly the user interface was there, right? It doesn't happen like that. My phone or my laptop, it takes ages to start up, right? It's worse. So what have we used it for? I've just added loads of stuff. The difference is my ZX81 just had a black, what was it, K or whatever it was, black square. That's all it has. Whereas this has all the graphics. What have we used it for? We've used all of this power for lots of graphics and lots of flash stuff and lots of abstraction, a higher level programming model, so that we can write huge amounts of software very, very fast and make it look nice, and we can have user interface people look at it rather than excessive techies like me, and just make it really nice and look nice. So we've got this new incredible high-performance processor, and we say, no, you can't do any of that. You can't do any of your high-level programming. You can't run any of the software that's inefficient. You can only write in really low-level languages. Well, if I'm writing in low-level languages, it's already running fast. I want to run Java. I want to run C#. I want to run Python, Haskell, Lisp. You know, that's what I want to run on the GPU, because that's the stuff that I really want to go faster. So we need to be able to do garbage collection. Okay, just as an example of how incredibly difficult this is. When can you do garbage collection? On a CPU, what you do is you choose particular points and go, right, okay, it's safe to do garbage collection now. I know where all my pointers are. You stop your program on the CPU and go, right, I'll search through all of the pointers, follow them, and get rid of everything. In fact, most of it happens in the background, but there's a point at which you need to go, right, stop. As the number of threads goes up, this gets really, really hard. There's a point at which you have to stop all of the threads. And if you have a few thousand of them, or a few 100,000 like you do on a GPU, stopping all of them is a bit of a problem, particularly as there is no way of stopping a thread on a GPU. Anyway. We can also build tools. Yeah, this is the other thing that's missing. So you do all really hard programming, like parallel programming on a GPU, which is really hard, and then you don't have the debugger. Oh, and you need to do performance optimization without a profiler. Oh, you're all students. I tell you, this is the worst thing that I ever get from researchers and students when I hire them. This is the thing that academics never teach students. Don't optimize without profiling your code. Does anyone get taught to use a profiler? No, you don't even know what it is. You're looking blank, right? When you really want to make something go fast, okay, as I have spent a lot of time doing, you need to see where the time is used up. Otherwise, you can spend a huge amount of time optimizing a particular loop, only to find out it only took a millionth of a second to run. It's something else that you hadn't thought of. It takes a minute. Or it's being run at the same time as something else, in which case it makes absolutely no difference optimizing it, because it's the slow thing. You've got to be able to analyze the performance before you do optimization. It's the first thing you do, anyway, and they never teach it in university. Right, yeah, I've had students, and you bring them in, and I've spent ages optimizing it. It didn't go any faster, and I don't know why. Did you run a profiler? Yeah, no, I didn't. So how do you know that you're optimizing the thing that's important? Right, okay. Parallelism in analysis tools. And what else? I mean, it's really hard doing parallel programming. And so we really want to have the tools to be able to analyze what's going on. Why is it not running fast, or why is it breaking? These new standards enable us to build those things. So I'd like to do that. So now what we can do is we can start to build whole new platforms, like really crazy platforms in some cases, that run stuff theoretically very fast. But because we run standard software platforms on top, we can actually run real software in a way that we could never do before. You know, you could go off and you could go, I'll design this fantastic parallel processor, and I'll write the only piece of software that ever gets written on it. There's a certain pointlessness to that, but some people do very well out of it. But you've got to write the one piece of software that makes your parallel processor worth it. And the question is, why did you bother designing a processor if it's only ever going to run one piece of software? Why didn't you just design it in silicon? So, part of what we need to do now is we need to decide what should these hardware platforms look like. And it's harder than it looks. So one of the big things is the memory model. You know, if we're not going to standardize a standard memory model, what the memory looks like, and yet the memory model is so important for performance and power consumption, how are we going to get anywhere? And then we have what form of parallelism matters. And then there's the argument about data parallelism versus MIMD. Right, I'll come to this. Right. This is one of the big issues that we have. It's nastier than it looks. So CPUs actually use memory management. They use virtual memory. And what happens is you have a page table in the operating system, and if a page of memory isn't in the virtual memory space, isn't in the physical memory space, then the operating system goes and loads it from disk, right? So what happens is your process stops, your application freezes. I mean, it's actually not a particularly nice thing, virtual memory. I mean, it's the thing that causes your applications to slow down. But anyway, what it does, it does mean you can have applications that use up huge amounts of memory. What it does is it goes and loads it from the disk. You can't actually, if a GPU gets to a point where it goes, oh, I'm accessing this data, and it isn't in physical memory, then what happens? How does the GPU say, interrupt the CPU, and the CPU goes and fetches that page in, sticks it in, and the GPU restarts? You know, if the GPU is doing the user interface, your user interface completely locks up, the whole system locks up. You also have the problem, if you have 1,000 threads, all requesting different pages, and they don't all fit in at the same time, how do you load all the pages? It may actually be impossible. The problem is, if you don't do that, you can't share pointers between the host and the device. If you can't share pointers, you can't share data structures, or you can't easily share data structures. So we have this incredibly hard problem above, and if we don't do that hard problem, the most basic thing, just being able to have pointers and data structures, doesn't work. It's quite nasty. Okay, this is the thing that I get into huge arguments about. Cache coherency, right? Cache coherency means if one core writes some data, it's going to write it into its cache, okay? And another core tries to read the same address. Where does it get it from? Does it get it from its own cache? In which case, the same address, it doesn't see it. It doesn't see the thing that the other core wrote. So what has to happen is the caches have to communicate, say, oh yeah, I wrote here. So the other one. Now what that does is it means that every core can read right after another one is written. And it makes sense. You assume, right, if you write to a variable in one thread and you read it in the other thread, you get the value written in the first one. In order to do that, every cache needs to broadcast every read and write to every other cache. That's n squared, I think, in the worst case. Somebody said it's exponential. I think it's n squared. Whatever it is, it's bad. Okay? So as you get, if you only have 4 cores, it's no problem. If you have 1,000 cores, n squared is generally bad, right? I got into an argument with people about the Laraby chip. So Intel said, you know what we're going to do is we're going to design a GPU based around x86 cores. We're going to do all the stuff in software. It's going to be entirely cache coherent. And it didn't work. Anyway, they finally released it as Xeon Phi, but they won't admit that you can't find out how big the chip is. It's absolutely massive, but no one knows quite how massive, but it is absolutely massive. The bus size that they need to stick on there in order to be able to communicate with cache coherency is absolutely crazy. So crazy that you can't buy them very easily, and it's a lot. So the question is, right, okay, so you just go, don't care about cache coherency. In a lot of cases, actually, cache coherency is completely useless because, in my experience, if you rely on cache coherency, you've got a bug because you should be locking. You should, if you're reading and writing a data structure, you need to do a mutex. You should be doing a lock. You shouldn't be just relying, oh, that thread wrote something, so this thread can read it. It's probably a bug, what you've got. It turns out the problem now is that cache coherency lets you start kernels running on another device very fast. Because what happens is you can instantly say to the other device, run this, and its cache will pull across the data from the other cache. Cache coherency will let you start very fast. It will run slower, but start faster. And that balancing act is an extremely tough one, because what happens is, as your caches get larger, if you have to flush your cache in order to start on another device, it's incredibly slow. And that makes it very expensive to move from one device to another. It's an extremely tough question to answer. And as the number of cores changes, as the software changes, you can't answer the question very easily. But it's fun to have arguments about. So the other thing which I maybe should have brought up earlier is that SIMD versus MIMD. So a GPU operates in this way. It's called single instruction, multiple data. So what happens is you have a single instruction and lots of ALUs, right, arithmetic logic units, execute this instruction in parallel. So the same as instruction is executed lots of times. And what that means is you only need one instruction decoder. And instruction decoders are expensive in terms of power and area. So that's how GPUs operate. They execute the same instruction huge numbers of times. It's extremely efficient. But the problem with it is if any thread, in that sense, needs to block, they all block. If any thread needs to do one thing, they all need to do the same thing, or they all need to go idle. So it's less efficient. It's a tough balancing act. Whereas in a MIMD device, that's multiple instruction, multiple data, that's like a multi-core processor. That's like normal threaded programming, like you would get in a server, web server, something like that. But there, you need an instruction decode unit for every ALU. So it's hugely less efficient to do the operations. But MIMD can do all of the threaded synchronization that you need to do. Now, the question is, can we do something halfway between those two? And if we don't standardize what we do halfway between those two, we can't build a standard platform on it. So what do we do? I'm not going to answer this question, but it's an interesting question, and it's interesting to see, can we find a balancing act between the two? Or are we just going to have two extreme cases, a CPU and a GPU, either ends of the spectrum? So finally, what can we build? So what's possible with massive amounts of computation power for very little power consumption? This is like an exercise for the listener, seeing as I have no idea. What are we going to do with it? I mean, it's really massive. Apple's answer is to put really, really crazy, actually Google did it well, crazy resolutions on a tablet that lasts for 20 hours on a single charge. One of the things that we may have to get used to is that visual user interfaces and camera interfaces may actually require more performance than the things that we're used to on our desktop. It's not unrealistic to think of a quite near future in which our phones and our tablets have more processing power by a long way than our laptops. If you think about the things that you want a portable device with you to do, its sensors are already more than you get on a laptop. Its wireless connectivity is already more than you get on a laptop. It's perfectly reasonable to say, a phone to be able to look around, and I'm terrible with names. If I lift my phone up and it goes, oh, you met this person before, he's called Kevin, right? That would be quite a good thing if I could do it surreptitiously, right? If I held up my laptop and did it, you'd think I was an idiot. But if you held up my phone, I could pretend to be receiving a phone call or something like that, which would be good for me. It is actually possible that could happen. The design effort going into mobile chips is such that we could have more of that processing power in a phone. The thing that upsets me is the only thing that's actually been advertised in phones along this line. Have you seen the stuff, the Galaxy S4? If you're watching a video, it tracks your eyes, and then if you look away, it pauses the video. That's the most disturbing thing ever. If you think they are going to put telly on there, right? They'll put telly on there, and the advert is going to stop when you look away. I'm going to do it with your TVs as well. So you're not looking at it, it's going, oh no, I'm going to stop. You're going to watch this advert. So I was thinking, do you have to have special masks that's got eyes on it to be able to pretend that you're watching the adverts? Right, okay, that's good because I've come to the end. Have I come to the end? Yeah, I have, right, okay, that's it. Where next? We have this need to move to greater parallelism to achieve more performance, and we have this incredible opportunity, and I'm hoping that we don't use that opportunity to have devices that force you to watch the adverts. Okay, any questions?
I want to hand over a microphone for one last question because otherwise it won't be recorded.
Actually, while the microphone's moving across, I will point out we are a really cool company to work for, and we do have some jobs at the moment. And so if you're interested in some of this stuff and would like to live in Scotland, it's quite a beautiful city, Edinburgh. It's cold, but anyway, it's nice. No, it is. It's cold. Actually, Cambridge is cold. It's no worse than Cambridge. It's prettier, though, I think. Yeah, go on.
Right, so my question was, it seems to me that with mobile programming, quite often you have like a virtual machine or something you can test it on. Do you know of anyone who's built like a virtual GPU on a computer? Because it seems like, I don't know if these questions could be answered if you could actually see what was going on. Like when my GPU crashes, I don't know what went wrong.
There are simulators. There's something called GPGPU sim. You don't want any of them. They're in nowhere near fast enough. So what's the point?
No, I mean when you're actually testing the code.
Yeah, but it's going to run slowly. I mean, by slowly, I mean really slowly. If you're going to emulate something that runs 1,000 threads at a time on something that runs 4, and you're doing an emulator, that's a big speed reduction. But there are simulators. They don't simulate a lot of real-world GPUs, and the problem is real-world GPUs are quite secret, and so it's quite hard to get an accurate simulator, certainly of a modern GPU. But if you're doing NVIDIA stuff, I think GPGPU sim does do. We do research projects with universities, and certainly they've been using that as part of it. And I think they've got the source code, so they can modify and add to it. So, but the question is, I think I mean, NVIDIA have quite a good debugger, don't they? I'd actually use it. It's better than you can use a simulator if you want. I'm just warning you. Expect it to be really slow. Yeah.
Hi. So one of the use cases I've heard mentioned for GPGPU is to enable you to do other things. So I guess I'm talking about a specific use case where you have a device with a CPU and a GPU. I'm talking about high computing generally. One of the examples I've heard is you could use a GPU, for example, to implement an improved physics engine for a game. But one thing that strikes me about that is that that's inevitably going to mean time spent on non-graphics computation, if you see what I mean. And I guess my question is, do you think that's going to take a paradigm shift in the games industry before people start doing that? Because the way it seems to me is that it's only going one way with games. When you buy a new game for your console, for example, you know, the selling point is the fact it's got a fancier model, better shaders. You know, it's going to take a brave games developer to say, all right, you know, it's not going to look as nice as another game that's been released, but it's got a nicer physics engine. Yeah,
that is the problem, basically. I mean, I did a lot of physics and computer games when I started, though it was a lot more basic in the 16-bit days. But you know, we also got involved with a company called Aegea, who actually started off a lot of this kind of general-purpose offloading stuff. They did a physics engine, and actually their chip. I should be careful if you're recording this. The problem with recording this, I won't say as much. But anyway, right. It wasn't quite like a GPU. So then NVIDIA and AMD said, no, we can do this on the GPU. And it's not quite so efficient doing it on the GPU. And exactly that point. And one of the problems is it doesn't necessarily use that much computation power for some of the box physics, the crate physics, right? Huge numbers of crates, we've all seen it. I've done it myself. Huge numbers of crates, and yeah, that physics. I think things like fluid physics is quite interesting. But the thing about fluid physics, if you look at it in games, is it's very easy to simulate lots of particles. So what you have is fluid physics using computational fluid dynamics, and then the problem is you get a huge number of particles. So you end up rendering lots of particles, and water doesn't look like lots of particles normally. There's a surface on it, and so what you need to do is calculate the surface. It's very unusual to see somebody who's done a decent job of calculating that surface. And the problem is a lot of that isn't data parallel and is often better on the CPU. And it is a problem where we had with bringing this stuff to games is that, yes, a lot of people are using it for the graphics, and there's a lot of processing that can be done in the graphics. Though a lot of what is being done is they use the standard triangle rendering to draw the scene, right? So you throw huge numbers of triangles at the screen and everything. And then what you do is you go over the whole scene doing more complicated lighting. And some of that stuff is getting extremely complicated. So if you've got the depth map and you've got all of the colors, you can actually work out a lot. You can work out, from all of the polygons that you can see, you can actually work out where it is in 3D space. So you can go over and process that, and you can do that in quite a data power way, and then do individual lighting on each pixel afterwards. And some of that stuff's getting very complicated. So the Frostbite people, EA Dice in Sweden, have done a lot of stuff on that, and then there's a researcher that I keep talking about in Munich who talks about that a lot from an academic point of view. And so it's still sometimes the same compiler technology, so it's the same from us. They may be writing it in OpenCL or something like that, but they are just using it for the graphics. See, and I would rather that some of this processing power was used for more physics and more, because I think it's more interesting. You know, seeing fantastic graphics is all very well, but if the interactions with the objects are not very interesting, then what's the point? Well, you never know, it's not as pretty as it could. There are people who will concentrate on a lot of different things, so some people will concentrate a lot on the physics. There's a game developer in Germany somewhere that concentrates on sand, and there was another one in Britain somewhere, I can't remember, that concentrated on water. And it does make it look different. I mean, that's the thing about if you just concentrate on one thing, you can end up with a game that looks very different. It's not. It doesn't. Yeah, it's not. It's a physics simulation, not. I mean, you know, the example that I always give with what I always wanted to do, I think Frontier did that here as well, was calculate animation of people and animals and stuff like that. And the people who took it to the extreme was Natural Motion, the Oxford company. And they did all sorts of stuff with it. So in Grand Theft Auto 4, the first use of it, in Grand Theft Auto 4, you're driving around cars into people, right? And they used it so that they can, if your car hits you, it looks like a realistic person being hit by a car. You know where they make all their money now? They do pony games. So they do these pink pony games where you dress up your pony and ribbons and things like that. That's where they make a fortune out of that. They sell all of that animation technology, and you know what they do? They sell the pink ribbon, and you can buy different coloured ribbons, and kids buy them, and they make a fortune out of it. They did what I wanted to do, which they did the sports game. They did American football game where, you know, the people crunch into each other, and it was quiet. I thought it was a good idea, but no, ponies. That's where the money is.
I actually like to ask if you could introduce yourself. The questions that one question was from you. Do you mind introducing yourself? Okay, at Cavendish. You are from Cavendish, and you work for. Okay, so next question.
Hi, William Stoy from Broadcom. The SIMD MIMD thing. Do you? I mean, it's science fiction. I mean, it's crystal ball gazing to try and decide where it will end up in the end. But do you notice a trend? Are they becoming more MIMD, the GPUs of today?
You put me on the spot there, haven't you? They are becoming more SIMD, but more SIMD, but more capable of looking like they're not. So they are more capable of doing strange branching. That's where it's going. They're more capable of doing strange jumping around, but the cores go idle. If they're not all executing the same instruction, they go idle.
Okay.
So that seems to me to be strange. So the full MIMD allows you to do locks and mutexes and synchronization and semaphores and stuff like that. And the problem is if you have 1,000 threads doing that, you are guaranteed deadlock. You are guaranteed for it to break in horrific ways. And you haven't got a debugger on a lot of these GPUs, so it's going to be bad. So that's the problem. Although MIMD would theoretically be better, I think, for a lot of applications, if you ignored the laws of physics. I think the problem is you might not actually be able to program it. But it's, in terms of where it's going to go in a few years' time, I think in the short term, I think SIMD is the way it's going. It's just not the way I want it to go.
This is Alan from Broadcom. It seems very mysterious, like a big secret, how a lot of these GPUs work internally.
Yeah.
You were saying that it's a fool's errand to optimize without profiling, and earlier we talked about how there are not very many good simulators. I mean, how are we to optimize for a mysterious platform that we can't simulate and don't understand the pipelining of? Moving forwards, I mean, specifically, unless developers are given this ability, how are we ever going to develop the advanced?
So the problems I get from software developers in terms of programming GPUs is, firstly, it would be extremely useful. They love tools that can sample what the GPU is doing and say, I'm spending a lot of time on this shader and this source line, or this OpenCL kernel and this source line, this function. That's extremely useful to them.
Sure. I'm thinking, if I may, though, more specifically, when the Cell was launched, IBM gave the Cell simulator out, and you could look cycle accurate at exactly where if you're familiar with cell processing, how your DMAs were going. You could look at your even odd pipelines. I mean, there's nothing remotely like that for the GPU in the public domain that I can see.
No, so I get a lot of complaints from my staff saying somebody at some point in Codeplay is going to write a program that just goes, right, these are my instructions, and does it. The problem is you need to know the instruction set for the GPU to do it. But there's a tool on the SPU which is incredibly useful. You give it your assembly language, and it does it cycle by cycle, shows you all the cycles. And when we write compilers, that would be an extremely useful tool to have. It just shows you, right, oh, there's a stall here, and it's this many cycles.
Sure, yeah, I mean, that's exactly
but
what
it's
I'm thinking
difficult
about,
unless you're going to expose your GPU instruction set, it's very difficult for a final software developer to make use of it.
Sure, and I understand that, but it does kind of seem like the hardware guys, I understand they want to keep this stuff secret so that the competitors, whoever it is, won't copy it off them. But on the flip side, unless the developers really understand and have the tools to work with this stuff, I mean, for example, to take one use case, to take real-time path tracing with engines like Brigade and stuff like this, Octane renderer, a lot of those guys seem to be stabbing around in the dark. They don't even understand what sort of percentage utilization they have of the hardware. And I know there's a few papers have been put out kind of speculating, well, look, these traversal algorithms that we have, are they any use? What are we at, 25% utilization, 75% utilization? We don't really know. And it just seems like, okay, you might kind of know to the order of magnitude where you are, but I mean, you can't really be taking these things seriously as a development platform until you have the basics like that.
Yeah. And some of the problems that we have at our level, that because the developers are not able to program an assembly language, they're programming with a compiler. And because the GPU instruction sets are so weird, they will complain to me that it's very hard for them to understand why one version of the shader runs twice as fast as another version. It doesn't seem to make any sense. And sometimes I've seen the source code of the compiler, and it doesn't make any sense. I know it doesn't make any sense. There's nothing you can say that it just does it that way. But then you have the problem as a developer. So why does this go twice as fast? Because I do it that, but then I'm missing this feature, or I thought I optimized. And that's very hard. That is a hard problem. And we've in the past done quite a lot to try and give feedback out of the compiler to explain to people, I did this, and this is why. And so we did this thing ages ago called the interactive optimizer, which you have the source code on the left and the assembly language on the right. Now, if you're not prepared to show the assembly language, it's a bit difficult, but at least so that you can fiddle around with the source code, and it gives you some warnings. So it had some warnings to explain, this is why I've done this, and this is why I've done that, and if you change this. Some of the problems from a compiler point of view are very hard, in that it's very hard to explain compiler alias analysis to people. Very hard. And that's something that's C is very dependent on alias analysis. So it can be very hard. But then other things like the level of precision, for example, can be very weird. The rules about precision can be very weird. But at least you can say to people, you know, I've done something odd with precision here. This is why. And even if you can't quite understand what it's saying, you at least know that there's a precision issue. At least give you something to narrow down on. That would be extremely useful. Those tools that analyze performance, some developers absolutely rave about them. There are certain analysis tools that tell you even how roughly what's going on. Game developers can really love them.
Sure, absolutely. I mean,
when it's a black box, they get very fed up, and they're just going, I have no idea what I'm doing here.
Yeah, no, I mean, just because in contrast to the CPU, where, you know, you have this established tool chain, a big part of that tool chain is, I mean, you can see what your bandwidth usage is, you can see where you're stalling on memory, then maybe you can go adjust your data structure, you can, you know, make an algorithmic change. The GPU, you're just kind of poking around in the dark, just hoping that you can infer what's happening. Once
the CPU gets to a very long pipeline, then you can have exactly the same problems. I've certainly spent a lot of time on Pentium 4 as the worst case, although I've heard of the more recent case that may have been designed in Cambridge, where you get very weird behavior with pipeline stalls. And that is a problem, and it would be very useful to understand why. But Pentium 4 is extremely unpleasant. I mean, you'd spend ages writing compiler optimizations. It would literally be half the size of code. In fact, maybe that would case about 3 times shorter, and it was slower. I have no idea why. Absolutely no idea why. So it's not entirely true that CPUs are different. It's just it's as the pipeline gets longer and more complicated, then it does get much worse.
We can take 2 more questions, I think, and then anyone else? Okay, so thank you very much. Sorry, you have a question? Okay.
Hi, Gordon Dean from Sagentia. So I've been working recently with high-speed DSPs and FPGAs doing sort of industrial signal processing and things. And it was interesting to see a lot of similarities in the complaints about tool chains and things, actually. I suppose what I'm interested in is, given the vast amount of development money going into GPUs now relative to some of those sort of more niche technologies, whether you can see this becoming deployable outside of sort of phones and games. Are GPUs going to change the way in which we build audio devices, for instance, or video, or industrial sensors, medical devices? And when is that going to be a kind of realistic proposition as opposed to academic research? Because it sounds like it's pretty hard work at the moment.
Yeah, so that is an interesting question. It is something very relevant because, of course, the phone SoCs have a lot of DSPs on them, which you could theoretically use for these things. The easiest example for me is the more similar one, which is currently on phone chips, there's not only a GPU, there's ISP, image synthesis processor, and they all have them. They're all completely different in a really weirdly different way. And they process the camera image and do all sorts of amazing things to it on a phone. Because the lenses on phones are terrible. I mean, look at the size of them, right? But they get processed a lot. And I think that there is going to be a move away from those. So what happens at the moment is if you buy an SoC, you pretty much get the photography software from them. Or you have to really specifically write it for them. And if you're a camera company who's wanting to do something new, you can do that in OpenCL now. And run it on the GPU. And the advantage of that is that you can independently innovate. You can come up with great new camera processing. It's slightly different with DSPs. You could, in theory, run, say, audio processing or signal processing on a GPU. But it would be potentially quite weird in that the timing constraints are different. A DSP is like signal in, signal out. It's very real time. It's very predictable real time. And also, I think the power consumption of DSPs is normally quite a lot less than that for a GPU for an equivalent task. It's just DSPs are quite basic. Yeah. Yeah. Yeah, so the main issue there at the moment would be control over the timing. A GPU is a pipeline. It doesn't happen instantly. It gets queued. And so you need to have a lot of data. You know, it's not just data in, data out. It's very much a pipeline. And so the question is, do DSP type tasks map to a GPU? And then you have the problem of, realistically, what you'd have to do is you'd have to standardize that. And there is some discussion about standardizing within mobile GPUs more the kind of things that you would do on a DSP, but like you described, a DSP that's doing a lot of processing. In some ways it's sticking a square peg into a round hole, but in other ways it does make sense to build such a thing on top of an existing standard platform rather than go off and say, let's do something else. I mean, the alternative is, you know, you build OpenCL and compile OpenCL for DSPs, and that's a question that no one quite has an answer to, but it would mean you'd be able to have standard platforms, and then, you know, OpenCL could maybe move more towards what DSPs are capable of. And that makes it easier for software developers to go off and try these things and ask the question, you know, here I've written my software, it would run on a GPU and it would run on a DSP, which is going to give me the best performance per watt, which is going to hit my target and not use up the battery too much or whatever it is. It's definitely yeah. I would say that it's probably more commercial research that's going on in that area than academic research.
Right, so a problem we have at the moment is performance portability. So if you're programming, say, an OpenCL, the optimal code for one GPU could be completely different from the optimal code from another GPU.
Yeah.
Do you think that's a problem with the immaturity of OpenCL backends, or are we just using a programming language at too low an abstraction level? Should we be programming at something higher level?
As a company that builds C++ compilers or is building a C++ compiler for GPUs that does this kind of thing, I would say what you need is a C++ compiler, and then your problem will be solved. I think it'll take you a long way. I think a higher level of abstraction would help with performance portability. I think that might start a debate. My experience, what you could do is you could say this is the performance model of a GPU, right? Everyone has got to hit this performance model. I think that would be a bad idea. I think there are good reasons why the performance models vary between different GPUs, because we don't know the answer yet, and some things are good at other things. But it is a problem as a developer. OpenCL says in it, it is not performance portable. It says in it, right? It's a design decision that OpenCL is not performance portable. Therefore, you have to adapt your kernels. So the next question you have is how? How are you going to rewrite your kernels for different devices, and how do you know what's good? How do you know how to change your kernel for different devices if you can't analyze it? And that's a very serious problem. What C++ gives you is, what the game developers do is that they have kind of abstraction layer. It's true of a lot of software developers. They create an abstraction layer to say, here is my performance model of this hardware and this hardware, and the templates transform it differently for different devices. And the advantage of doing it in C++ with templates is any developer can do it. It's not a compiler. So your compiler is just C++. It's not doing anything special. The template, so that a developer can always drill through. And that's my experience, is that developers need to be able to drill through. But there is an argument, and you know, I've talked to a very prominent software developer who does a lot of OpenCL stuff, and they've said they do a lot of kernels and they don't really care that much, the fact that it might run a bit faster on that. As long as it's not more than a factor of 2 or 4 difference, it's not such a big deal. I think it depends on how much you really want to squeeze the maximum performance out. But I don't think that what you're going to see is GPUs that are more similar in performance terms, especially in mobile. I think in mobile, you're going to see them more different. And in desktop, the GPU market is a bit of a problem. So I think, a high level of abstraction. And there are others who will say a higher level of abstraction as well. And the advantage of these standards is it makes it easier for us to build higher levels of abstraction, not just the one that we're doing, which is C++, but also other ones as well.
I think we are out of time. We have to leave the building by 6 o'clock, but if I'm right, Andrew, might stay around in the lounge.
No, I'm staying around. I'm going nowhere, yeah.
About 10, 20 minutes. But
yes.
If you want to speak to Andrew or to anyone else in the audience, please make your way out to the lounge. We have to empty the room and try to leave the building before 6 o'clock. We've got about 25 minutes now. But thank you very much, Andrew. Together.